So next we will see the first example of statistical estimation. And I will write it down as an explicit problem. Okay, so suppose we have n samples. Think of samples as just being data points. Let's call them x1, x2 up to xn that are drawn from a Gaussian distribution with mean mu and variance sigma squared. So this is standard notation for the Gaussian. It's a script n. N stands for normal. Okay, and we have n samples from this. We don't know mu and sigma square. And the goal is to estimate the value of mu and sigma. Okay, so this is a very basic question in statistics. Okay, so and this is as you can see, this is the quintessential example of going from data, which is your x's data that you've seen, to saying something about the process that generated it. In this case, we want to find the mean and variance of the process that generated this. Okay, so this is one of the most basic problems of statistical estimation. Okay, and note that earlier we used to talk about like some random variables drawn from this, and now I'm talking about samples. Okay, and what you should realize is that x1 is one real sample drawn from this random variable n mu sigma squared, and this is often also called a realization of a random variable. Okay, and yeah, so this is what we call as a realization of a random variable. Now, so the first intuitive answer, so now the question is, how do you estimate mu and sigma? Right, so for mu, the most intuitive estimate for mu is simply the empirical average, right? Because you have this distribution, which is the normal distribution, and you get a bunch of points. Let's say these are your points. Okay, and if you want to estimate the mean mu of this distribution, the natural thing is to take the sample average. Okay, so the most natural estimate is simply the sample average. And this way of finding out or approximating the mean, so this is what is called an estimator. Okay, formally an estimator so this is of an estimator for some parameter let's call it mu, is a function of the observations. Okay, this is very similar to this notion of a statistic that we have seen before. right? So if you remember, if you get n IID samples from a distribution, we said that a statistic is just some function t of x1 through xn. Okay? An estimator is basically the same thing, but now you have realizations of this random variables, okay, x1 through xn. Okay, and so now the question is this a good estimator for the mean? So is this average a good estimator for the mean? Okay. So before going there, one thing I forgot to mention is that the difference between an estimator and the statistic is simply that in one case you really have something that you would like to estimate. In the other cases, a statistic can just be a quantity of interest. You don't really, you may not be using it to actually estimate some parameter of your distribution. Okay. So that's the main difference between an estimator and a statistic. All right, so okay, let's get to this question, which is this a good estimator for the mean? So the first thing that you should notice right off the bat, okay, so the first observation is that any guarantee that you can hope for, which is saying that this quantity is close to the mean, has to be probabilistic in nature. What do we mean by that? Means that there is always a chance that we are unlucky. A chance that we are unlucky and the estimator is off. Estimator value is far from the true mean. Okay, so this, as you can imagine, is quite likely if you have a very small number of samples, right? So let's say I have to estimate the mean and I have only two numbers, right? So let's say I have this Gaussian, this is a mean. Now there is some reasonable chance that maybe I pick my 2 points happen to be on this side, right? Because being on either side is equally likely. And so with probability 1/4, both my points will lie on the left of this mean, in which case this estimate is going to be pretty far. The mean of these two, the empirical mean of these two, so this is my x1 and this is my x2. So x1 plus x2 by 2, this is the quantity I will call the empirical mean. So this quantity lies way to the left of this mu, right? So this is quite plausible, right? And in this case, we are in some sense unlucky. Okay? But now, as you can imagine, if you take more samples, okay, your estimate is going to get better. Okay, so in the case of the mean, this observation is what is called the law of large numbers. So we won't cover it explicitly, but it's a very useful fact to know. And it basically says that estimates of the mean, estimates get better, often get better if we take more samples. Okay, specifically this says something about the mean. Okay, so let's not go into the formal statement. You should refer to the textbook if you are interested. We will actually see some variant of this later on. Okay, so that's the first point. Okay, so there is always some chance that we are unlucky and the estimator value is quite far from the true mu. Okay, so this is one observation. Okay, so our goal then is we would like an estimator, we want the estimator to be as close as possible to the true value, right? So to be close to mu with a high probability. So this is one thing that we want. Okay, and this quantity, so this is called the variance of this estimator. We will define it formally. The estimator should be low. Okay, so we'll define this a bit more formally later, but this is intuitively the reasoning. Okay, so we would like this estimator to be close to what it's supposed to estimate with a pretty high probability. Okay, now the other goal is that the estimator, at least if you take lots and lots of estimates, right? So now what you can imagine is, suppose I have an estimator. Let's say this is my estimator. Okay, I pick one one set of data points, okay, and these are drawn according to this Gaussian. I compute this estimator. Okay, so the second requirement. Okay, so suppose I pick one collection of data points. So let's say x1, x2, x3 up to n, xn, and I compute this estimator. Okay, compute estimator. Let me denote it by mu hat. Okay, so this is just the average of these numbers. This is how we normally denote the estimator. So it's an estimate for mu. It's often denoted by mu hat. Okay, now let's say I repeat this experiment. Okay, so repeat this experiment. Okay, and I get a new mu hat. Okay, new mu hat. Okay, and then I keep doing this. Okay, so keep doing this. Now, and suppose I do it like a very, very large number of times. Okay, now I would like to have that the average of these estimators, like the average of these estimators to be very close to mu, right? Okay, and so in effect what we are saying is that if we look, in effect, if we look at the expected value of this estimator. So what does that mean? So now, so let's not look at the samples themselves, but let's view each sample as the random variable. Okay, so if I have x1, x2 up to xn, where each is simply a random variable, this is a random variable distributed as n mu sigma squared, right? So the ith sample is going to be, as we said before, this is going to be a realization of this random variable, right? So now what we are saying is that if I look at these random variables, now I take this new random variable which I call the which is the average of these n random variables. So that's x1 plus x2 up to xn by n. So let's call this y, right? So this is a statistic, right? So y is a statistic of our, this is basically the average statistic like we saw before. Now what we are saying is that the expected value of y must be equal to mu. Okay, so this is the statistic that you are computing. This is the estimator that you have, and we would like the expected value of this estimator to be equal to mu. Okay, and so this is not true for all estimators. It happens to be true for the mean. But the difference between these two quantities is what is known as the bias of an estimator. Of an estimator is, let's call it T. okay, just to keep in notation with the statistic, is simply estimator t for quantity for parameter theta. So theta is like mu in this case, okay, is defined to be the expected value of t minus mu. Okay. It doesn't matter, sometimes people might define it as mu minus expected value of t. Okay. So so this is called the bias, right? So turns out that in this case the bias is 0. If the bias is 0, this is called an unbiased estimator. T is called an unbiased estimator. Okay, and so these are like the basic definitions. Okay. So next week, next class rather, we will look at unbiased estimators for the means, and we will also formally define this notion of a variance, and we'll try to see which estimators are better than the others and so on by taking a bunch of examples. Okay, all right, let's stop here for now.